In the early days of computing, loading a program was an exercise in pure geometry. Through a method called contiguous memory allocation, a complete application was placed cleanly into RAM as a single, unbroken block. That works perfectly until the system gets busy. As you open applications, you close them, and open new ones, memory starts to resemble Swiss cheese. You are left with scattered, isolated gaps of empty space sitting between active programs. This diagram shows exactly where that process breaks down. Here, a 16 kilobyte program is trying to load into a system that technically has 20 kilobytes of total free space. But because that free space is split into 5 disconnected chunks, the system freezes. The program has enough total room, but no single continuous space large enough to fit it. This paralyzed state is called external fragmentation. To keep systems running smoothly under heavy workloads, operating systems had to abandon the idea of storing programs in continuous, solid blocks. To stop the computer from choking on its own wasted memory, engineers had to make a choice. They could divide memory by conforming strictly to the physical limits of the hardware, or they could divide it by respecting the logical, human-designed structure of the software itself. The first approach is physical. It's called paging. The operating system ignores what a program actually does, chopping logical memory into fixed-size pieces called pages. Physical RAM is similarly sliced into identical slots called frames. These uniform blocks are highly standardized. Often, a single page and its matching frame are exactly 4 kilobytes in size. Because every single block is identical, these pages can be scattered smoothly into any available frame anywhere in physical memory. By breaking the program down into standardized parts, external fragmentation is completely eliminated. This mapping chart, called a page table, acts as the operating system's internal GPS. It links these sequentially numbered logical pages on the left to completely randomized physical frames on the right, allowing the system to instantly locate every scattered piece of your data. But fixed sizes have a mathematical flaw. If a process requires 10 kilobytes of memory, the system must allocate 3 4-kilobyte pages. That equals 12 kilobytes of allocated space, which leaves exactly 2 kilobytes of empty space permanently trapped inside that final block. This trapped void is called internal fragmentation. By prioritizing rigid physical space, paging guarantees that invisible, unusable waste will build up right inside the system's own boundaries. So what happens if we abandon the rigid math entirely and divide memory based on human-defined meaning? This is segmentation. Instead of fixed boxes, programs are broken into logical, variable-sized units, reflecting their architecture, like code, data, and a stack. To keep track of these pieces, the operating system maintains a segment table. Each entry records a base address, meaning where the segment starts in physical memory, and a limit, which defines its exact, varying size. This logical view perfectly aligns with how developers write software. It makes modular programming simple, allowing different processes to share code easily while keeping specific data securely protected in isolated segments. But because segment sizes are completely variable, their constant loading and unloading eventually recreates the exact same scattered gaps in RAM that we saw at the very beginning. Segmentation honors human logic and software design, but it fails to eradicate the original crisis. Over time, those variable blocks will inevitably lead right back to external fragmentation. The engineering dilemma is strict. Do you accept the internal waste of fixed pages or the external gaps of variable segments? Advanced modern operating systems solve this by refusing to choose. They use both. This diagram illustrates the combined process. First, the system uses segmentation to divide the program logically by function. Then, it applies paging to ruthlessly chop those specific logical segments into uniform, fixed physical frames. By layering the two paradigms, the system eliminates external fragmentation across RAM, while still perfectly preserving the logical organization that programmers rely on to build secure applications. This invisible address translation requires heavy lifting. To keep your applications running smoothly, the operating system performs this mapping sequence millions of times every single second in the background. This high-speed balancing act between physical hardware limits and logical software structure forms the foundation of virtual memory. By mastering both space and meaning, modern computing becomes possible.